Gradient descent and the delta rule. Several algorithms exist to solve the running problem, that is learning the weights of the perceptron. So we have already seen there were two different types of training rule. One is the perceptron rule, the second one is the delta rule. Coming to the perceptron rule finds a successful weight vectors when the training examples are linearly separable. That is, the perceptron rule fails to converge if the training examples are not linearly separable. Coming to the difference between the training examples that are linearly separable and non-linearly separable. So we'll consider here with some data points and classified here some other data points. When I consider these two data training examples, they are linearly separable. So these type of training examples, they are called as linearly separable, whereas there exists some data points which are not linearly separable, because these two are the data points. So we need something, okay, which is going to classify these separately and these as together as one group. So there the training examples are not or linearly not separable. Here the training examples are linearly separable. So the perceptron rule works fine for the training examples that are linearly separable, but not for the training examples which are not linearly separable. That is, fail to converge if the examples are not linearly separable. So we'll take up the next type of rule, that is called as delta rule. The delta rule, it is designed to overcome the problem that we saw above. So it is, if the training examples are not linearly separable, the delta rule converges towards a best fit approximation to the target concept. So we use data rule or the delta rule for this type of training example. This delta rule, it is also called as withdraw and off learning rule or least mean square rule, that is called as LMS rule. And this delta rule, it works by using the concept or the algorithm that is called as the gradient descent algorithm. The key idea behind the delta rule is to use the gradient descent to search the hypothesis space of all possible weight vectors to find the weights that best fit the training example. So why this rule is important? Gradient descent provides the basis for the backpropagation algorithm, which can learn network with many interconnected units. Till now, we are just talking about a single perceptron, a single unit. When we consider a neural network consists of many interconnected units. So we need a backpropagation algorithm. The backpropagation algorithm works with the help of the gradient descent algorithm. Second, the gradient descent can serve as the basis for learning algorithms that must search through the hypothesis space containing many different types of continuously parameterized hypotheses. Gradient descent and the delta rule. The delta rule is best understood by considering the task of training an unthreshold perceptron, that is the linear unit for which the output O is given by. So X represents the input vector, the weight vector, and again the input vector. So the gradient descent or the delta rule, this works well for the unthresholded perceptron. Unthresholded perceptron, it is nothing but the linear unit. So when we considered the perceptron, it consists of inputs x1, x2, up to xn, the weight w1, w2, and so on up to wn. We did summation. So we got the value that is z. So it is I equals to 1 to n wi into xi plus b. So this is called as the unthresholded perceptron. So this was once again processed through the activation function. So we are not going to take the output that is processed through the activation function. So whatever the output we got from this perceptron up to here, it is called as the unthresholded perceptron. That is, this is called as the linear activation function. So the delta training rule is best understood by considering the training task of training and unthresholded perceptron, that is a linear unit for which the output O is given as this one, that is with x is a vector here, input vector, which is equal to w into xi. Thus, a linear unit corresponds to the first stage of the perceptron without what? Without the threshold. When we'll get the threshold? When we process this through the activation function. So without the threshold, whatever the output we are going to consider, so that corresponds to the linear unit, that is the first stage of the perceptron. To derive the learning rule for the linear units, so we are talking about only the linear units, that is unthresholded perceptron. Consider a training error of hypothesis, that is a weight vector related to the training examples, where the training error is given with the formula E of the weight vector, which is equal to 1 by 2 summation of small d belongs to capital D, TD minus of OD all to the power of square. So this is called as the training error, where whatever we have here, this is considered as the cost or error function, and what we have here, this gives the loss function. The training error of the hypothesis, this is what the gradient descent. The gradient descent always gives the cost of the error function. So the error function will be using this, where capital D is a set of training examples. TD is the target output for the training example D. OD is the output of the linear unit for the training example D. Here, E of vector W is simply what? Half the squared difference between what? The target output TD and the linear output, that is OD, summed over all the training examples. So D belongs to capital D, sum over all the training example. We consider the loss function. So this is what the training error of a hypothesis we are going to consider related to the training examples. Now visualizing the hypothesis space, since we are using the gradient descent, okay, gradient descent search determines a weight vector that minimizes what? That is the error function E by starting with an arbitrary initial vector weight, then repeatedly modifying it in small steps. So how the gradient descent works is, so we have the training. So in the previous slide, we can see here the training error. So what the gradient descent does is, so it minimizes the value of E. Initially, it will consider some weight. Okay, I'll suppose consider some weight, that is W1. Initially consider the weight is W1. We assume some weight. So what the gradient descent does it, fine. It will go on modifying this weight in small steps. Okay, which is nothing but it goes on reducing what? The error of this weight in small steps. So at each step, the weight vector is altered in the direction that produces the steepest descent along the error surface. Each time it will consider a weight, it will find the error, it will see if the error is more, again it will perform the operation. Like this, it will go on reducing what? The error until it reaches to this particular point. The process continues until the global minimum error is mu. It is nothing but it is minimizing the error. When it reaches here, it is nothing but the error is minimized. So somewhere the weight of W1, consider somewhere the weight of W1 is here, that is old of Wi. So each time it moves to the direction that produces to the steepest descent until it reaches what? The global minimum, which is minimizing the error. So this is what? This is the new Wi. So gradient is nothing but derivative. So the derivative of V with respect to what? With respect to the weights is what we are doing. So that is called as the gradient descent algorithm. So which minimizes what? Which minimizes the error. The process continues until the global minimum error is reached. It is nothing but minimize the error. And this is done by using the rule or the delta rule given as Wi equals to Wi plus delta of Wi, where delta of Wi equals to minus of the learning rate and the derivative of E with respect to the derivative of Wi, where here E is what? E is the error function. We take the derivative of E, that is the error function, with respect to the Wi, that is with respect to the weights. Then each time the value of the weights keeps changing in smaller steps, moving towards the direction that produces the steepest descent along the error surface until this global minimum error is reached. So this is the old weight and this is the new weight. So we'll see the derivation of the gradient descent rule. So how can we calculate the direction of the steepest descent along the error surface? So this can be found by computing the derivative of E with respect to each component of the vector, that is the weight vector. This vector derivative is called the gradient of E with respect to the weights. So this is written as the gradient of E with respect to what? With respect to the weight vector. So the gradient of the error with respect to weight vector is given as, okay, derivative of E with respect to the weight 0, derivative of E with respect to weight 1, then and so on, partial derivative of E with respect to the weight n, which is nothing but these are the partial derivatives of E with respect to which one? With respect to weight Wi. So in the previous we saw that is Wi is nothing but Wi plus of delta Wi, where the delta Wi, where the delta Wi is given as what? Minus of the learning rate, then derivative of E with respect to derivative of Wi. So this is what is evaluated here. Okay, expanded here. When interpreted as a vector in weight space, the gradient descent specifies the direction that produces the steepest increase in E. The negative of this vector therefore gives the direction of the steepest decrease, because we need to decrease the error or minimize the error. Hence, we are taking the negative of this vector, therefore gives what? The direction of the steepest increase. Since the gradient specifies the direction of the steepest increase in E, the training rule of the gradient descent is written as same thing here, minus of mu, then the gradient of E with respect to the weight vector, which is nothing but I wrote here what? Derivative of E with respect to what? That is Wi, where the learning rate is a positive constant learning rate, which determines the step size in the gradient descent search, and negative sign move the vector in the direction that decreases what? That decreases the error each time. Hence, we are considering here what? The negative sign. The training rule or the delta training rule can be written as the same thing. The new weight is updated by using the old weight plus delta of Wi, where this delta of Wi is given as negative of the learning rate with respect to, that is the derivative of the error with respect to the weight vectors, that is derivative of Wi. The vector of, okay, derivative of E with respect to Wi derivatives form the gradient can be obtained by differentiating E from the equation. So we have the cost function or the error function that is given, that is E of with respect to what? The weight vector, that is the error function by considering the weight vector equals to 1 by 2 sigma of D belongs to D, TD minus OD all the square. Fine. Now the derivative of E with respect to derivative of the weight, that is Wi, equals to the derivative of, fine. So here we considered what? Derivative of E by what? Derivative of Wi. So this is the cost function or the error function. The cost function or the error function with respect to the weight is given as what? 1 by 2 sigma of D belongs to D, TD minus of OD whole square. So that is what I have substituted here, 1 by 2 sigma of D belongs to D, TD minus OD whole square. Now this half I will remove here, then sigma of D belongs to D. So we have the derivative of TD minus OD whole square divided by derivative with respect to Wi. Now again you consider here, so when you just give the derivation or differentiate this, that is differentiation TD minus OD of whole square divided by derivative of Wi. Differentiate this, we'll get 1 by 2, that is sigma of D divided by 2. This 2 into TD minus OD, then the derivative of TD minus OD with respect to what? That is weight. Here TD is what? A constant, fine, and here OD. So you already know that is the output of the linear unit, the output of the perceptron for the unthresholded perceptron, that is output with respect to the input vector is equal to what? Is equal to W vector into X vector. So this is what we know. So here what we'll do for this, we'll replace with the value, that is W vector, that is into X vector, that is D. So replace the value for this one. So now do the differentiation, okay, Wi and Wi. So this will be differentiated for the last value here, and TD is what? TD is what? A constant value. When you do the differentiation, the finally we get sigma of D belongs to D, TD minus OD. So we have the negation here. So this is Wi, this is D. So this is for the training example, but this works well for what now? W1 into X1, W2 into X2 and so on. So everything is a constant. The last value that is left out is what? Wi into Xi for the training example, that is D. So this is what is differentiated for this weight. So we get minus of X ID. So this is what negative sign of XID. So the derivative of V with respect to the weight Wi equals to summation of D belongs to D, TD minus OD minus of XID, where this term denotes a single input component Xi from the training example B. Now what we'll do, we'll consider this and we'll substitute this value in this equation. That is, we had Wi, that is Wi plus of delta Wi, where this delta Wi equals to negative of the learning rate, derivative of the error function with respect to the weight I. So we got the value for this. So this is nothing but derivative of the error function for the weight vector. So when you substitute this value, we got what? Sigma of D belongs to D TD minus of OD. So this is called as the delta rule for learning the perceptron. So we'll consider the gradient descent algorithm for the training or for training the linear units. The gradient descent algorithm consists of the training examples and the learning rate. The first step is initialize each Wi, each weight to some smaller random value. Step 2, until the termination condition is met. 2, initialize each delta of Wi to 0. For each training example, 2, input the instance X to the unit and compute what? Compute the output, that is O. For each linear unit weight Wi, do what? Do calculate this value. Delta Wi is what? Delta Wi plus of, that is the learning rate, T minus O into Xi. For each linear unit, finally what you do Wi, update the new weight with the old weight plus of delta Wi. So you will take the delta Wi value as what? Delta Wi equals to delta Wi plus of the learning rate T minus O into Xi. Coming to the next, we have stochastic approximation to gradient descent. Previously, we saw the standard gradient descent algorithm. Here we'll see how it is different from the stochastic approximation to the gradient descent. Gradient descent is an important general paradigm for learning. It is a strategy for searching through a large or infinite hypothesis space that can be applied whenever. The first one is the hypothesis space contains continuously parameterized hypothesis, that is the weights in the linear unit. The second, the error can be differentiated with respect to the hypothesis parameters. Difficulties in applying the gradient descent are converging to the local minimum can sometimes be quite slow. If there are multiple local minima in the error surface, then there is no guarantee that the procedure will find the global minimum. So the variation of the descent, the gradient descent, it is called as the incremental gradient descent or the stochastic gradient descent. In gradient descent, the rule represented is what? Delta Wi equals to the learning rate, the sigma D belongs to D, TD minus OD into XDI. So it is nothing but, so this value, it is considered for all the training example. The summation of all the training examples for this is what is calculated. Computes the weight updates after summing over all the training example that is done. The idea behind the stochastic gradient descent is to approximate this gradient descent search by updating the weights incrementally. It is nothing but consider the first training example, then increment the weight. Consider the second training example, then increment the weight. Consider the example, then increment the weight. Whereas it is not the case with the gradient descent. In the gradient descent, so this is computed for all the training examples. Then what? Then the weight were updated in which type? In the standard gradient descent, which is different from the stochastic approximation. The idea behind the stochastic gradient descent is to approximate this gradient descent search by updating the weights incrementally following the calculation of the error for each individual example. For each individual example, we'll calculate the error. So that is delta Wi equals to the learning rate of T minus O into Xi, which is almost similar to your perceptron training rule, where T is the target value, O is the output obtained from the perceptron, Xi is the ith input for the training example in question. So the difference between the standard gradient descent and stochastic gradient descent are the error is summed over all the training examples before updating the weights. It is nothing but the error is summed over considering D belongs to D, then T minus O square, then into Xi. Whereas here the weights are updated upon examining each training example. More computation per weight update steps are required, less computation per step because summing over multiple examples. Larger step size per weight update, smaller step size per weight update. Then in case where there are multiple local minima with respect to the error for with respect to the vector, weight vector does not avoid falling into these local minima. Sometimes avoid falling into these local minima in case of multiple local minima. So these are some of the difference between the standard gradient descent and stochastic gradient descent.